The type 2 error for differences in means is a little bit more complicated if we have the restricted case of knowing that the variances are available to us, and in terms of the population sizes, and also if the sample size from both populations are the same, then things get down to a reasonable complexity. But when we're talking about this T statistic that we were dealing with where variances aren't known, then some other things are going to happen to us here. So let's talk a little bit about how we might approach the case of estimating the type 2 error. And remember that that is the situation where we fail to reject the null hypothesis when it turns out that the null hypothesis is false. We were somewhat preciously close to that in our example where we just barely met our p-value barely met our criteria of the 5% level, and even that from a practical standpoint you might want to go ahead and reject that. So we're going to talk about this a little bit in further detail and some of the problems or issues that arise in this kind of a case. Right? And one of the big ones here is that the distribution of our test statistic when our variances aren't the same is not known if the null hypothesis is false. That's a crucial one for us. And now we're going to complicate things here and say that, and we do not know sigma 1 nor sigma 2. And so whether those two are the same or whether the difference, we don't know them anyways, and under the conditions of H null being false, we don't know what this distribution is going to be. Right? So what we could do is make a wild, crazy guess. Do all the things that we're not supposed to do. In other words, right? If you look at the operating characteristic curves in your textbook, back in the appendix, charts 7G and H are one-sided t-tests with alpha equaling 0.05 and 0.01. G is for 0.05 and H is for 0.01. E and F, the two that come right before that, are two-sided t-tests with alpha equal to 0.05 and 0.01. And it's on those charts that we can read off directly what the beta value is for our probability of a type 2 error. Right? The problem here is that these charts were set up to be used with or under the scenario that our two population variances are the same, even though that they're not known, but they're the same. Right, now we might be able to accept that maybe they are the same even though they're not known, but the other condition is that our sample sizes are the same. Right, and they weren't in this case. Now they were pretty close to each other, and you could try to play a game and this wild crazy guess of saying, well, okay, hey, I can take care of that, I'll just get rid of two of the extra ones out of one of them, the data sets, and then n1 equals n2. Well, yeah, you could do that, but how are you going to know which ones to choose? Do you choose the two outer ones, as in the min and the max? You could if you really thought those are outliers, but what if they're not outliers? What do you do? So that choice of which ones to randomly choose is kind of tough. Well, maybe that's the key, right? You randomly choose which ones to get rid of. I guess you could do that, and you could even play a game of running the exercise multiple times by choosing different different ones and seeing from a sensitivity kind of standpoint if it really makes much of a difference. Right, that'd be one approach that you could. Another approach might be to in essence use sort of a pooled kind of approach, and you could, presuming that your variances were known, you could define a pooled n by weighting essentially by the variances. Right? Do that as opposed to just averaging the two. Okay, you could use our approach of, in essence, n equaling the degrees of freedom that we got out of our equation 1016 out of your book, and that was just simply the one that looked somewhat similar to this, where we instead have an s here, we substitute in the sample, we square each of these terms, square the numerator, that was to get our degrees of freedom. We'll actually get relatively similar degrees of freedom out of that. Now remember, in the usage of our operating characteristic curves, in that sort of non-dimensional view that they have back there, then this d that we're going to need is defined as the absolute value of delta minus delta naught divided by 2 sigma. Right? And again, in a very crude kind of fashion here, this isn't really the right thing to do, but if we sort of put blinders on, do the dumb thing, just use it anyways, see what happens, play a game, then the observed difference in the sample means was minus 205.3. The delta 0 from the null hypothesis in that case was 0, and then 2 divided by the standard deviation that we were working with was 113.97. When we do that, we get a d value of 0.9. Right? And so if we used 15 from our degrees of freedom for our n, use 0.9 here, when we go into the operating characteristic curve, and I'm going to show that directly out of the book. This is on page 720 if you have the hard copy. Note that we can then come in at d equal to 0.9 up to, and at the tip of my little paper envelope opener, n equal to 15, and read off that our beta value is just a little bit less than 0.5, maybe about 0.04. And that's from chart 7G. That beta is approximately 0.04. Whether that's large or small depends upon a lot of other factors. So, big picture though, as we look at this example, you'd almost have to come down on the conclusion that we don't have enough evidence to reject our null hypothesis. That yes, you could at the 5% level, but you look at the 95% confidence interval on the difference in the true means, it includes this value of 0 and a lot of other sort of small negative values. You look at how as you go from 5% to 1%, you're very sensitive to moving from statistically significant to not statistically significant, and you also look at if we use the null hypothesis that the difference was equal to negative 100 of pseudo-practical kind of value, and then you don't have you don't at all have a chance to reject it even at the 1% level. Then you pretty much, I think, have to conclude that there's not really quite enough just based upon these two samples to conclude that there's a significant difference. So what do? Well, you can always increase the sample size, right? Because that is a driving influence in these sample measures. That if we look at that aspect of it, expend more money on the testing, and if it really matters to us to demonstrate that there is a significant difference, and if that difference of say 200 psi in the tensile strength is important, then it's probably worth it. But probably, well, that it brings in a whole lot of other questions, and many of which are business questions, and not just purely a statistical question that has to be brought to bear.